You know, the very first clue we had that our universe is expanding came from light, specifically the light from really distant galaxies. When we look at it, we notice it's been shifted toward the red end of the spectrum. We call this redshift. Now, the common explanation you always hear is that space itself is stretching, and it's literally pulling those light waves, making them longer.
And that idea, it kind of makes sense, right? But hang on a second. If expanding space can stretch something as fundamental as a photon, it leads to a pretty wild question. What about other stuff? What about an atom, a planet, a star? What about you? Are you, sitting there right now, ever so slightly expanding along with the universe?
Well, to get to the bottom of that, we have to dig a little deeper into what redshift actually is. Because the real answer, it turns out, is a whole lot weirder and way more interesting than just saying space is stretching.
To really crack this, we need to look at a key piece of evidence. See, physicists don't just talk about one kind of redshift. They actually talk about 3 different kinds. And while they all seem totally separate at first, understanding how they connect is the secret to figuring this all out.
Okay, so first up, you've got the one we all know, Doppler redshift. It's just like where an ambulance siren sounds lower as it drives away from you. Simple enough. Then there's gravitational redshift, where gravity itself messes with the wavelength of light. And finally, we have cosmological redshift, the big one we see from those faraway galaxies. 3 different effects, right? Well, maybe not.
Let's zoom in on that gravitational redshift for a sec. Back in 1959, there was this brilliant experiment at Harvard where they fired photons up a 22-meter tower. And get this, by the time the photons got to the top, their wavelength was just a tiny bit longer. They had been redshifted. It was a minuscule effect, but it proved Einstein's general relativity was right. The weird part is, it seems like the photon is just getting tired as it climbs up.
So why does that happen? How can gravity tire out a photon? Well, to understand it, we need to pull out one of Einstein's biggest ideas, the equivalence principle. This is the master key that's going to let us look at that tower experiment in a whole new light.
So here's the big idea, and it's so simple it's profound. Standing still here on Earth is physically identical, indistinguishable, from being inside a rocket out in deep space that's accelerating upwards at 9.8 meters per second squared. From inside that rocket, you'd have no way of telling the difference. This lets us swap gravity for acceleration, and that little switch, well, it changes everything. All right, let's hop into our imaginary rocket and run the experiment again. A blue photon gets fired from the back of the rocket, right at the moment it starts accelerating. For someone inside that rocket, the photon looks green by the time it's halfway across, and by the time it hits the detector at the front, it's measured as red. It's the exact same result as the tower experiment on Earth, but what's causing it here?
But here's the really cool part. What does someone just floating in space outside the rocket see? To them, nothing special happens. The photon just travels through empty space and stays blue the whole time. So wait, how can the photon be both red and blue? The answer is beautifully simple. The observer inside the rocket is accelerating away from the spot where that photon was created. What they're actually measuring is just a good old-fashioned Doppler shift. And this right here, this is the whole game. It reveals a fundamental truth about the universe. Redshift isn't something that happens to a photon. A photon doesn't get stretched or lose energy on its own. Redshift is a measurement. It's a property of the relationship between the thing that emitted the light and the thing that observed it.
Okay, so if gravitational redshift is really just Doppler shift in a clever disguise, what about the big one, cosmological redshift? To understand that, we just have to apply this exact same logic, but on the scale of the entire universe.
And to do that, we really have to zoom out, not just past our solar system or even the Milky Way. We need to go past our entire local group of galaxies.
We have to zoom out so far that the billions and billions of individual galaxies just blur together. They become like tiny specks, like molecules, in a vast, smooth, uniform substance that physicists like to call the cosmic fluid. Now, when you're looking at the universe on this massive scale, it has these 3 key properties. It's homogeneous, which just means it's basically the same everywhere. It's isotropic, meaning it looks the same no matter which direction you look, and of course, it's expanding. The density of this cosmic fluid is going down over time.
Now, to make sense of this, let's imagine a special kind of observer. Imagine observers who are perfectly still within this cosmic fluid. They're not moving through it, they're just being carried along with the expansion.
We call these co-moving observers, and they are our perfect measuring sticks for the universe.
And this brings us to a completely new way of thinking about cosmological redshift. Imagine a photon traveling from a distant galaxy to us, and imagine a long line of these co-moving observers all along its path. Because the universe is expanding, each observer in that line is moving away from the one before it. So if they were to pass that photon along like a baton in a relay race, each and every handoff would add one more tiny little Doppler shift. The total cosmological redshift we measure isn't from space stretching the photon, it's simply the sum of all those tiny Doppler shifts added up over billions of light years.
Okay, we've totally reframed this. We've seen that all three types of redshift are basically just the result of relative motion between a source and an observer. There's no need for some mysterious stretching space. And with this powerful new perspective, we can finally and confidently answer our original question.
So, after all that, let's ask it one more time. Are you expanding along with the universe?
The answer is a big, fat, definitive no!
And here's the deal. Remember that whole cosmic fluid thing? Those assumptions of a smooth, uniform universe? They only work on the biggest scales. Down here, on the scale of a person, or the Earth, or even our entire galaxy, things are lumpy and messy. Your local bit of spacetime is completely dominated by the gravity of Earth. But even more importantly, your body is held together by electromagnetic forces, and those forces are trillions upon trillions of times stronger than the incredibly subtle effect of cosmic expansion. The same goes for atoms, stars, and even whole galaxies. They are bound systems and they're not going anywhere.
So that popular idea of expanding space being some kind of active force that's constantly pulling and stretching things apart, it's a really powerful mental picture, but it's just not what's happening. It's a useful way to visualize redshift over cosmic distances for sure, but it's not a physical force that's pulling on you right now.
So if there's one thing you take away from all this, it should be this. Redshift isn't something that happens to a photon on its trip through the cosmos. It's simply a measurement that pops out of the relationship, the relative motion and gravity, between the thing that sends the light and the thing that sees it. In the end, those three types of redshift, they're really just different views of the exact same phenomenon.
But of course, solving one mystery just opens up another, even bigger one. If cosmic expansion isn't an active force that pulls things apart, then what in the world is dark energy, the mysterious stuff that's making the expansion speed up, actually doing to the fabric of spacetime? But that's a story for another explainer.